Thanks for joining this session, Navigating Chaos. Hopefully for the rest of the folks who are late, they are not stuck in traffic due to some of the attacks that we're going to explore today. My name is Vesto Jari. I'm a VP of Engineering at DigiCert. Background, mostly being a hacker. Now I build solutions that are protecting some of the problems that I caused in the past.
Hi, everyone. My name is George Gunter. I'm a fifth-year PhD candidate at Vanderbilt University in the civil engineering department, and I come from a little bit of a different background than many of you. I study transportation science, and particularly I study intelligent transportation systems, so transportation with computation, and I'm hoping to bring a little bit of transportation education to you all and think about how we're thinking through some of the cybersecurity issues that you all are working on solutions to.
Great. Let's begin with some backgrounds. Some of you might be already familiar with this, but vehicles have been compromised for quite some time. Matter of fact, all the way back to 2010, a few researchers at University of Washington identified that they're able to put a malicious payload, put it inside the vehicle's entertainment system, and then they could cause brakes. They could be able to basically accelerate the vehicle, do a number of different things. This was interesting, but required a kind of a physical access to that vehicle. Fast forward to 2015, two researchers, not from the academia, but from the industry, were able to remotely compromise a Jeep Grand Cherokee. They were able to basically drive the car remotely, cause a number of different kind of unaccepted behaviors on that vehicle. I'm going to take your attention in the movie that came out recently called Leave the World Behind. And there's a very specific scene in this movie that all of us found very interesting. Well, though this scene may sound a little bit science fiction, is actually quite real. It's possible to be able to do these type of attacks due to a few components that exist on the cars that could be compromised. It's not only vehicles. Matter of fact, any connected devices, and we generally call these embedded devices where they have connectivity via internet or internal networks, could be compromised. There are a few examples here. You can see a thermostat, you can see a PLC or programmable logic controller, you can see a medical device that I spent almost a decade breaking into them. But the problem is that as we are introducing new components, specifically in the case of vehicles, such as sensors, radars or LiDARs or whatever that might be, we are also introducing a sense of insecurity if that introduction happens too quickly. Let's talk about the vehicle's nervous system, or we call it CAN bus, Controlled Area Network, for a second. Every single vehicle that anybody has driven since 1995 utilizes a CAN bus. CAN bus enables you to be able to send signals from your brake system to your accelerometer to your emission system, whatever that might be, and communicates the different components that we call ECUs, electronic control units. These ECUs are in charge of different capabilities that goes into the car. On average, today, a modern car has around 70 different ECUs for different use cases and different functionalities that they have. Some of these components could be, again, a sensor that you may have. This would be an ECU that could utilize for navigation system if you have an autonomous vehicle. Or it could be a camera that looks at the traffic in front and behind you, and we see this in some of the modern vehicle manufacturers. Let's grab a specific component for this presentation, and that is ACC. ACC stands for Adaptive Cruise Control. Most of us have utilized cruise controls, very simple. You'll go ahead and indirectly utilize a sensor that is on the car. You give it some input. That input goes to the control unit. Input will be your speed, 70 miles per hour, 80 miles per hour, as well as the distance that you're going to keep between your car and the car in front of you. Well, that has kind of evolved throughout the years. It's a little bit more than that. The newer systems enables you to actually switch lane. They'll make sure that you stay in a specific lane. And these are all the capabilities that ACC, or Adaptive Cruise Control, has gone through in the past few years. Now, there are two categories of vehicles that we are usually dealing with in 2024 that could utilize ACC. The top category is an autonomous vehicle. There's a vehicle that has capability of switching lanes, but it doesn't have a capability of going outside of in the exit, if you're taking an exit on a highway. The second category could be a connected vehicle that is also somewhat autonomous, that has a capability of communicating with other vehicles, but also could take an exit, could drive inside the regular streets, and per se is not only for highway use. The newer category that you guys may have seen here in San Francisco is a connected vehicle that is also autonomous, and this is fully autonomous. I saw one of these last night at the stop sign. There is no individual inside the car. Is being connected to remotely, has a number of different sensors, could make turns, could identify the traffic, and so forth. Now, all of this together goes into different categories that George will describe, that what we are considering a vehicle and their functionalities.
Yeah, thank you, Avesta. So while traditionally security experts might think about things in terms of the single vehicle, transportation engineers really think about things at the level of our infrastructure systems. We think about systems of vehicles. So in particular, I want to introduce two ideas here. The first being a useful scale to talk about levels of automation in traffic flows. And this is called the Society of Automotive Engineers automation level. And it starts at 0, referring to vehicles that are controlled exclusively by a human, all the way up to full self-driving, where humans may ride in the vehicle, but they have no input or no control over the vehicle. In addition to that, a useful definition to talk about is what's known as mixed autonomy traffic flow. So 40 years ago, traffic flows were exclusively human control. We were at exclusively level 0. Going into the future, we now have traffic flows that have a mix of human-driven vehicles, still most vehicles are controlled just by humans, and automated vehicles. And in particular, the automated vehicles lie in many different portions of this SAE spectrum. And it's estimated right now that for most commercially available vehicles, we're sitting somewhere in between 2 and 3. So this is your standard adaptive cruise control, plus maybe now some extra things with respect to lane changing. So getting further up the line, but we believe we sit roughly here, although after being in San Francisco, I'm starting to think maybe 5 should be of more consideration, which would be sort of the Waymo vehicles that we're seeing. Although a point I want to make is that for 5 to be true self-driving, you have to really trust that vehicle can do every single thing you would expect a human driving vehicle to be able to do. So some question of whether it's there yet, but very close. So this is sort of just to center everyone in terms of how we're thinking about systems of automated vehicles at the transportation system level. So I'm going to show a video here in a second, and just to center you, this video is trying to emphasize the extent to which when we design algorithms for automated vehicles, they can have influences not just on how that vehicle in particular drives, but because of the following nature of traffic, they can influence other vehicles. And so I'm going to show you an experiment done in 2017 that shows an example of an automated vehicle controlling a traffic flow through the design of its algorithm. And so it's going to show a ring road of vehicles following each other and how that vehicle's algorithm is going to influence this broader traffic flow. So we start in a ring, so start from stop, and every vehicle is controlled by a human at this point. One of these vehicles has automated capacities. And as the traffic flow progresses, you're going to see this wave start. This is a traffic wave that's going to travel in the traffic, and this is something that we see in many traffic flows in real life. And at a certain point, the automated vehicle is going to turn on a piece of software where it's going to regulate its own speed specifically to make sure that it can try and stop these waves. And so we're just showing here sort of the speeds of all these vehicles. And you can see that in this period where there's this wave, there is high variance in the speed that's doing a lot of stop and starting, and that as the automated vehicle controls, it's able to smooth out these waves. And so this was sort of a pioneering experiment that showed that we could do great things with designing these algorithms, but that I want to try and flip that discussion to talk about, given that there is this kind of control nature that even a single vehicle can exhibit, are we comfortable with that given that it could be flipped to do something negative? So just to further that discussion, I'm going to play another video that shows another experiment, this time where a set of commercially available adaptive cruise control vehicles are all following one vehicle that's going to execute a small braking maneuver, and we're going to see their response. So on the left, we're going to show some drone footage of these vehicles, and on the right is a time series plot of the speed, and it will evolve over time. So first, this sort of test vehicle, a probe vehicle, is going to go that's just going to execute a braking event. And every vehicle after that is an adaptive cruise control running commercially available software. And at this time, the vehicle at the front is going to brake by not very much, so around 5 miles per hour over 10 seconds or so. And what we're going to see is that progressively, every single vehicle that is adaptive cruise control is going to amplify that braking event, causing more and more significant braking patterns, until by the time we get to the very end vehicle, this was in 2019, at that time, these vehicles would only operate at about 20 miles per hour. And so the point being that there are these emergent behaviors from these kinds of control algorithms that are very important at the transportation level. And it's not a given that when we think about how these algorithms are being designed and coming into deployment, that they are necessarily beneficial for traffic flows. So I won't make us watch this again. OK, final point for background videos. These kind of traffic waves don't just exist in sort of ring roads, but this is footage from a freeway outside Nashville, Tennessee, which is where Vanderbilt is. And what I want to draw your attention to is if you look up here, you can see the sort of waves start and then form and then move back in the traffic flow over time with vehicles stopping and starting. And so this is just sort of an example to emphasize that these are real things that we're really concerned about. And they're known to decrease efficiency. They're known to decrease safety. They increase emissions. These are really undesirable things to have. And what I want to, the thought that I want to put in your head as we progress is, can you tell what caused this? It starts all the way up here, and by the time that you're a vehicle driving through this, your only option really is to just try and not have a collision. You can't really say very much about where this came from. So this is a very undesirable emergent behavior that we have from our transportation systems. Just to complete the transportation system background, you all are going to be experts in reading transportation diagrams by the end of this presentation. An important diagram that I'm going to show is what's called a space-time diagram. It's not very complicated, but the idea is if we have a vehicle on the left and we have its distance along a road plotted over time, as it moves along at the speed limit, we can then draw its position and shade it with respect to its speed, so just showing that it progresses over time. And then as it stops, we can shade it again with respect to its speed and have it go again. And so this is what we call a space-time diagram. And when we plot many of these such trajectories from a set of vehicles, it helps us look at overall traffic flows. So I'm going to show you many instances of this kind of idea. So to begin, here's an example of, again, some of these trajectories that come from the same freeway that we were just looking at. So if we shade all of them with respect to their speed, we can see position, time, and that an emergent behavior that we see are these traveling traffic waves, that an important idea is that they move both in space and time. They're a wave with their own speed, with their own behavior. And just to sort of drive this home, this would be an example maybe of one trajectory for one vehicle where it progresses at a certain speed, stops, it has to go through this wave, and then can progress again. And so, an interesting question here would be, can we tell what's causing these waves? Can you say definitively that those aren't caused by some sort of poorly performing automated vehicle? Probably not in this case, because we don't think these are happening right now, but maybe. So, all right, progressing, I'm going to hand this back to Avesta.
All right, this is the aha moment where you have a traffic engineer and a hacker coming together and figuring out that we can create, or potentially we can be able to create some type of a micro-braking in the system if we compromise a vehicle that has an autonomous system that is going to either create a collision, create massive amount of traffic, or even could be capable of stopping vehicles in the middle of the road or push them out of the road. Now, looking at this from our motivation, we know that the CAN bus has been compromised multiple different times. Matter of fact, CAN bus is the easiest network to be compromised because it lacks authentication. CAN bus is a broadcasted network in a sense, or protocol, where you have all of these electronic control units sending the signals, pump the brake, speed up, slow down, whatever that might be. And often it's considered that if there is a level of authentication on ECUs in CAN bus, the whole network will be slowed down. Well, that was a 90s idea. Fast forward a few years later, researchers have came up with different type of protocols that are capable of authenticating these electronic control units, But we took advantage that in 2024, these are still not authenticated. So we looked at two specific ideas with CAN bus. One, are we able to provide a software update to a CAN bus to cause these micro-breakings? Well, the answer later will be yes. Are we able to basically create a supply chain attack where an electronic control unit has been shipped through a supply chain to the dealer to be installed on your vehicle, and that ECU could also be malicious where it could cause these type of micro-breakings? Now, there's two ideas when it comes to these type of attacks. One, it has to be impactful, meaning it still has to cause those concepts of micro-breaking that we go through. And second, it has to be stealthy. Braking is not a catastrophic factor when it comes to driving. All of us brake every time that we drive. But the fact that we're able to make micro-braking and still keeping it stealthy is the meat of this work and allows us to be able to create these traffics. So we began our experiments by driving two different vehicles for the duration of 90 minutes. We did our recording of the CAN bus. We did this with different driving behaviors, basically trying to get as many data points as possible from these vehicles. We collected 30,000 CAN bus packets, and then we put these in a simulation. We didn't want to go to another vehicle first. So we basically simulated a CAN environment with Raspberry Pis, commercially available, with Arduinos, with a few different transistors, and we basically recreated a component of the vehicle, but in the lab environment. Now, George was smart enough to say, this is in the lab, but are we able to do this in a real vehicle? Which I will hand it back to him.
Sure. So just as we progress, I want to introduce a sort of thought experiment attack model that we can use in the rest of the talk to try and think about why we might care about this idea. It's a very simple idea. We call it a randomized deceleration attack, and it just would mean perform a brake check at a random point. And I want to be clear that the motivation for this attack is that it's extremely simple. So you could think of all sorts of different ways you might try to formulate ways for vehicles to do things. You might that could be impactful in different ways. This one's going to be a starting point that is simply impactful but simple. And the idea is just that if we can compromise one of these vehicles and cause it to brake, that you might be able to create these kinds of traffic congestion waves that I was just talking about. We don't use any sensors on the vehicle. We don't try to use the state. We don't try to formulate a complicated algorithm to use that as a feedback mechanism. You certainly could, and depending on what you think your level of compromise is, you probably should if you were an attacker. And it's not the only possible attack that one could formulate in this idea or in this context, but that the idea is that it has a mechanism to try and cause these kinds of waves, and that the creation of these waves leads to degradation of our traffic flow systems. So I'm going to refer to randomized deceleration attacks throughout the rest of the talk, just as a thought experiment to think through this idea. Okay, so a question worth asking is, should we actually be concerned about this capacity on real vehicles? So in our lab, we have a commercially available adaptive cruise control that we have augmented in a number of different ways to try and use for control. And so while for our research purposes, we obviously are not interested in trying to legitimately cause traffic jams, it does serve as a nice way to try and emulate this idea. And in particular, what we do is that we have a combination of software and hardware that we physically put into the car that allows us to do CAN bus read and overwrites. And in particular, it sits between the adaptive cruise control module on the vehicle. So this vehicle has cameras and things that it's using to try and create control inputs, and the rest of the car that is actually doing low-level braking and gas, and that we're able to sit right in between there and overwrite different command controls. And that this is the way that we want to try and think through, if you could have such a compromise, here's how we think it could plausibly work. I don't want to say that we think this is necessarily easy to do. We just want to show that if you had this level of compromise, that what would happen. And so we take our vehicle, we take our compromise, and then we take our algorithm and we put it on. So we have our compromise, our random deceleration attack, and we just took it out to a stretch of road where we didn't have anybody else around. We're obviously not interested in trying to create dangerous traffic environments, but we just did exactly what we said we were going to do. And so what you'll see is that we have the vehicle driving at around 40 miles per hour. We then send at a certain point, at about 12 seconds here, a constant braking event. So this is negative 1.7 meters per second, which is a relatively noticeable braking event. And what you'll see is that as we send it over time, the vehicle accepts this command input and adjusts its speed accordingly. And so this is what you might think of when you think of like what this looks like for these different compromises. And so I think the salient point here is that this is one adaptive cruise control vehicle and a compromise, but that when we go through all this trouble to actually make it so that these messages can be sent, nothing on the vehicle was able to catch this and overwrite it. So some reason to be concerned in that context. I don't want to oversell that point, but just some motivation for why we might be interested in these kinds of attacks. Okay. The rest of the talk is really going to focus on how we think we could go about trying to address some of these issues. And in particular, the first step that we want to try and motivate is that we are interested in trying to have ways to decide whether or not vehicles are exhibiting compromised behavior or not. So let's get started. So we've established that we have an attack that we're interested in trying to study. And in particular, the detection problem that we believe is most salient here is which vehicles are compromised. So in particular, looking at a set of vehicles, can we say when we think one vehicle or multiple vehicles are compromised? And I just want to point out that this is a different problem than saying, do I think a traffic flow is exhibiting something anomalous, which is something that transportation engineers already do, but that there's not really any mechanism when you look at a big picture transportation system to say, even if you think something anomalous is happening, to narrow that down into saying, was there a compromise on this vehicle, which is really the most direct question that we want to try and solve. And a fair question would be, well, if I know what this attack looks like, why don't I just filter for this in particular? And so while this is one particular attack that we formulated, an adversary might think of a completely different approach. And so we're interested in trying to do this in a way, do this without formulating a specific instance of what we think that attack looks like. So basically, I want to look at all of the vehicles, and I want to decide, do any of them exhibit malicious behavior? OK, so how do we think this could possibly happen? So first of all, we need to have access to data from individual vehicles. Data that just traffic flow data would not be sufficient. And so in particular, the kind of data that we want to use here is our trajectory data, meaning positions over time, which is exactly what I showed you previously. And thankfully, this is something that is becoming increasingly more available through GPS measurements. And so we want to look at taking GPS measurements that come from vehicles where perhaps there are some vehicles that are human-driven, there are some vehicles that might be compromised, there are some vehicles that just exhibit potentially normal automated features. And we need to try and take all of this data in and decide whether we think any of these vehicles are compromised or not. So how do we do that? This is really the meat of the talk and the specific method that we're proposing here. OK, so given this kind of data, these trajectory data, we're going to take this in and conglomerate it. And so we need to look at all of these trajectories together at the same time. And in particular, we're going to apply machine learning algorithms from cutting-edge techniques. In particular, we propose applying auto-encoding neural networks to solve this problem. And the reason that we choose this particular approach is that, one, auto-encoding neural networks are semi-supervised learning techniques. So that means that they can take in data coming from a benign space, so normal traffic in this case, traffic we don't think is compromised, and then they're able to form coherent representations of that traffic flow. And two, they're shown to work well with time series data, which is the kind of data that we're working with here. So in particular, we're going to take this and we're going to train auto-encoding neural networks, which we can then apply to that trajectory data. From there, these then allow us to do to create metrics of anomaly, which we're going to refer to as, which are specifically reconstruction error, but I'm going to refer to just as an anomaly score throughout the rest of the work. But basically, it will tell us, given a trajectory that I haven't seen before, how anomalous do I think that trajectory looks? And based on that, we can then perform classification and hopefully decide whether we think a given vehicle's behavior was anomalous. OK. Just to motivate this, let's go back to the ring road environment that I showed you earlier, the experiments with the vehicles in a ring. Just to summarize, we're going to use autoencoding neural networks to try and solve this problem. This is a semi-supervised approach, which in particular, as I said previously, is going to mean that we are not assuming any sort of initial attack structure. We're open to any kind of attack. And that the specific data that we want to work with here are GPS measurements, which are individual vehicle trajectories. This is going to allow us to look at vehicles at the individual scale. Okay, so going forward, let's take a motivating look at the data coming from the ring road. Okay, so this is the same data that you saw in video form, but this time shown sort of so that transportation engineers can read it. And in particular, what you're seeing is that in that period before the automated vehicle was activated, which here is this dashed line. And just to remind you, this is a ring road. Obviously, it's an experimental setup, but this is very useful for us trying to visualize and understand basic transportation problems. That we have this traveling wave that forms and moves, and I've just wrapped it around, so this is all the same wave. And that as we activate our vehicle, we're able to effectively smooth it, where, again, things are shaded with respect to speed, and this just shows the speed for all vehicles and that it smooths over time. So this is just showing some of the data. And so the question that I want to start with is, if we think this is a coherent way to approach this problem, can our approach look at this and say, there was an automated vehicle here that was doing something anomalous, can I find it? And the way that we're going to do that is that we're going to take our normal data, this data where it's just human drivers exhibiting this undesirable emergent behavior, we're going to train our anomaly detection in this context, and then we're going to test it in this context. And the answer is yes. It is able to effectively determine that there was an automated vehicle there exhibiting an anomalous behavior. And so I've just shown these are now shaded with respect to our anomaly score, so it just shows over time what is how anomalous I think those trajectories are. And so there's some variance over in this context where there's this wave. And interestingly, as it smooths things out, it actually brings down this variance, except for in red is shown the automated vehicle. And in particular, we see these spikes as it exhibits this behavior that go above the rest of the vehicles. And this in particular is what enables us to do classification and to say automatically, this is anomalous behavior. Okay, so this is just to motivate the idea that we have a setup that is going to allow us to try and effectively identify anomalous vehicles automatically in traffic flow. This is not for, per se, a compromised vehicle, but it's for an anomalous vehicle. And so the question that we want to then answer is, how do we actually analyze this for sort of meaningful traffic flows? And so we propose the following framework for how we can try and do that in an ethical way. Obviously, it's not really possible to go out and engage these attacks in real traffic flows and measure the effect. But what we can do is we can leverage significant work from the transportation engineering community in that they have developed, high fidelity, very accurate simulation environments that are able to take in models for how vehicles drive and create comprehensive traffic flow models that exhibit all these different kinds of behavior. And so these are just to show a few of the things that would go into trying to create one of these models. And that in particular, they've had a great amount of success recently in terms of designing algorithms for automated vehicles and tying them to how traffic flows evolve over time. And so this is a really attractive way for us to start trying to understand our problem in a safe context. So how does this work? Well, okay, so from here, we can get the equivalent of GPS trajectories because we can extract those automatically, and we can quantify how well a certain traffic flow is performing in terms of its efficiency or safety. And then to try and then to piece on our particular problem, this is also then a really easy place for us to say, I'm now able to specify algorithms for automated vehicles. Let me specify a model for how a compromised vehicle might behave. And so in particular, it's actually quite easy for us to define our random decelerized attack model in this context. And so we're going to piece on to this more standard micro-simulation environment, which looks at individual vehicles, a capacity to model attacks. And then finally, given that we can then simulate these sort of traffic flows that have both automated vehicles, human drivers, and compromised automated vehicles, we can then take this back to applying our standard, our proposed approach for trying to do anomaly detection that involves applying our auto-encoding neural networks and classification. And so basically, the idea is that we can take advantage of these simulation environments that exhibit a lot of the same kinds of emergent behavior that we see in real traffic flows and utilize this to do safe analysis of this kind of behavior. This is all open source software that if you are interested in trying to explore, it's here. It's also, we call it Anti-Flow, which is a little bit of a joke based on some other software, but this is the name of the software. It's all available online. So moving forward, let's now look at some examples of deploying this framework onto some examples. So let's look at, again, this idea of the ring road now in our adversarial context. So now we're actually able to look at what happens when there are real compromised vehicles, or simulated compromised vehicles. So here's just sort of a simple rendering of this kind of environment. And so the idea is that this is built using the kind of simulation tools that we use. And what you can see is in the same way that in the traffic flow that you saw previously, we have waves that emerge and move in the traffic flow. We have that same behavior. So again, I've just shaded now these dots, which are cars with the particular speed, so you can sort of visualize the motion of these waves as they go around. So again, the idea is that it's simulating a real-world traffic flow. And so a question that you should ask in this context is, as a human watching this, can you tell if there is an attack? So this is sort of like why this is potentially an extremely difficult question for us to solve in a non-automated way, is that if you needed to look at all these different vehicles behaving in this emergent way, it's extremely difficult to try and say what's going on here. Okay, so now let's look at another example. So we now have something that has a similar structure in that there's an emergent wave here and that it moves throughout the traffic flow. And in this case, it's actually a stronger wave. And so the question is, maybe I'm a traffic operator and I notice that there's something anomalous going on. I might be able to flag this, but then again, am I able to actually look at all these vehicles and say, okay, I can say that this one is anomalous. And so just to answer the question for you, this is sort of the comparison between the two, and you can get a sense of, in this context in which there is a stronger wave, there is an attack, which is sort of the point, is that this attack that we propose is able to create this kind of emergent behavior that is undesirable. And over here, there's no such attack. But there's not a great mechanism for, through your eyes, to say, okay, I can say that, well, actually, you can kind of tell here, that's the anomalous vehicle. But you can imagine that if you scaled this up to the question of a freeway, this gets very, very complicated. And so to drive home the need for good methodologies for doing this kind of detection, let's look at this data in our space-time diagram format. And so we can see, again, this sort of idea that we have these waves that move. The large white lines here just are they're because we introduced automated vehicles here that have somewhat larger following gaps than the human-driven vehicles, which you might have noticed the Waymo vehicles do that too. If I take this data and then I run my detection algorithm through it, I can plot the same idea, but now shading with respect to anomaly score. And the thing that I want to point out is if low anomaly is dark, notice the extent to which it's able to say, none of these vehicles look particularly anomalous to me. And then moving to now an example in which we have our compromise, we can see first that this is what it looks like when there is this sort of emergent, new, chaotic behavior, and that running through it automatically, this is actually, our algorithm is able to easily determine that this is anomalous. And in particular, it has the attractive feature that it even finds the specific places in space-time where it's executing these kinds of attacks and that this is anomalous. And so you see that in these examples, it's shading these with respect to shading these vehicles with high anomaly score, so it's able to accurately identify these vehicles as anomalous. And interestingly, when we increase the complexity of our environment, so this is an example. As we increase the complexity environment, so one might imagine that you can now have a two-lane ring road environment, and we're building up our environmental complexity to now account for lane changes, which is obviously desirable. We now have sort of, as our environment changes, we have differences in terms of the wave structures that are more complicated, and this leads to changes in how our anomaly scores are assigned, but that and additionally, that as the attacks now work in this environment, they create different coherent structures in terms of the waves that emerge. We're still able to sort through this and find examples in which we can automatically identify that there are anomalously behaving vehicles. And so this is just to highlight sort of the success of this algorithm in terms of being able to automatically learn from benign traffic data in which we think there's normal behavior and apply it to compromised traffic to quickly identify where we think these automated vehicles could be exhibiting these behaviors. So I'm going to hand it off to Vesta to finish this out.
So all of this work that George has done could have been prevented in a sense, because what was the motivation for this? If we couldn't compromise a vehicle to create these micro breakings, basically it wouldn't be any traffics caused by this attack, it wouldn't be any other devices that potentially could follow the same type of attack. So let's summarize this really quickly. We compromised vehicles utilizing their existing networks. We basically did a record and replay attack where we modified the replayed CAN buses to cause the micro-breaking. We worked on a detection solution, which was the meat of this job, utilizing machine learning and AI to be able to identify if there is a stealthy or a compromised vehicle in a traffic that is causing the traffic. And finally, this has the real-world feasibility. We can't, with a high probability, say that none of the vehicles that are around us have been compromised. If they were compromised, their behavior probably would have been, in a sense, the behavior would have been different. That would have caused a lot of different type of accidents and so forth. We saw the video at the beginning, and I mentioned that this doesn't sound so science fiction, because there is a possibility that these vehicles could be remotely compromised. Somebody could drive them remotely and cause those type of accidents. But in our case, even cause of traffic is considered to be a very massive compromise, because a nation state could do this in order for you to consume more gas. And that's a real world case that we're planning to study in the future. Now, some of the recommendations. Let's start with reevaluating the embedded devices and how they have to be secured. Interconnected devices are insecure, either being programmable logic controllers, being IoT devices, or the vehicles that we drive. They haven't been designed with security in mind. There are a few different security factors that could be applied here. For example, if the ECUs were utilizing authentication protocols, either based on PKI or they were utilizing code signing, which some newer vehicles do, but not to the extreme, we wouldn't be able to do our record and replay attack on the CAN bus. You should consider the connected devices, such as vehicles, to be a threat vector. I think as security professionals, we usually consider threat vectors to be our networking switches and IDPs or phishing attacks or malicious insider and so forth, but the vehicle by itself will also be a threat vector. Analyzing multi-agent systems at the agent level, this is where we are getting into the detection level. If you are considering any AI or ML approach solutions, this is an important factor for you. And finally, education, training, and maintaining the security posture plays a specific role for specific use cases. One size doesn't fit all. You can go ahead and apply an IDP, intrusion detection prevention solution in a vehicle. It just doesn't have the bandwidth for it. But you will be able to come up with authentication solutions to authenticate these electronic control units to prevent a similar attack. With that in mind, thanks for attending. If there are any questions, George and I will be happy to answer those.
Very good presentation. I like it. There's a little subtlety, and I haven't seen the movie, but there's a little subtlety that the malevolent actor is Elon Musk, but because it's a Jeep that's not affected, so it's funny, pretty funny. I've got two questions, and the one is based on a posit that I heard about 6 years ago at one of the first presentations here at RSA about attacking vehicles, and it was the team that attacked the Jeep.
Yeah,
in a parking lot, right? And the conjecture then was that we wouldn't have wide legal acceptance of autonomous vehicles on the road until the first accident between a human driver and an autonomous vehicle has been resolved. Do you think that's still true today? Is that still the limiting factor for wide acceptance of?
So with 100% probability, we don't know if any of the accident that has been caused by an autonomous vehicle was due to being compromised or not being able to just following the autonomous vehicle, blueprint. I mentioned that I worked on medical devices, and there is no specific evidence that shows that a medical device has been compromised that has caused a patient's death. If that happens, the FDA will be out of business in a sense, right? So similarly, from my point of view, I don't think this is something that has been proven yet, but is a possibility like anything else in security.
I think, yeah, great question. Another thing to keep in mind is that there's a difference between, for instance, full self-driving vehicles and automated vehicles, and an important thing for this talk is that basically every vehicle sold now to people have level 2 or level 3 automation on them. They have adaptive cruise control. And the important instance of that is the attack vector that we're talking about, is basically that there are ECUs that send control messages to the vehicles, and that's what's going to allow us to potentially get in there and create compromises. And so I think that even if we're still questioning whether there are like really instances of automated vehicles creating collisions in the full self-driving context, I'm sure there are examples of adaptive cruise control vehicles, for instance, being involved in accidents.
Well, yeah, I don't know, I'll say infamous one where the guy had let his vehicle self-drive and it was driving into the sun in the early morning and it couldn't distinguish a white tractor trailer and beheaded the guy. So, but the point of my question was less about whether or not the vehicle had been compromised or not, but it was more a question of whether or not the gating factor in wider acceptance is the resolution of the first legal question of fault between a human driver and an autonomous vehicle, because there probably was no malevolence in the tractor-trailer accident, but you had to resolve the cause there. Right?
I think that question is very, very interesting, because recently I read that the position for insurance companies, if you are driving a fully autonomous vehicle and it gets to an accident, as a driver, is it my fault or is my vehicle's fault that has done this? I think the complexity around this is just growing by the day. We don't have proper regulations. We don't have the right literature that guide us to figure it out what the problem here is. I kind of look at it from a security perspective. If my vehicle is compromised and I have no idea that it's compromised, am I at fault, or is the device manufacturer or the vehicle manufacturer has enabled this? And if I cause an accident, now this becomes a bigger question. Right. Whose liability is this? So.
Yep. And kind of a follow-up question, which is kind of to the point of the talk, right? The mixed autonomy. I like that word though. That's funny. Wouldn't you be able to consider inattentive or low-skilled drivers, in essence, being compromised vehicles?
Yeah, that's a tough question. If that driver behavior showed up in your training data and you decided that it was important enough to really factor into the training, then you would have models that would learn that behavior as being normal. And so, yeah, that could definitely influence the extent to which they would let compromised automated vehicles pass. I think that going into the future, this is certainly something that we should account for, is trying to understand ways to not let these algorithms be too unduly influenced by bad drivers, so drivers who are texting or something like that, in terms of how that influences our training algorithm. But yeah, it certainly could. I think there's also a more complicated question of, if you were the defense in this context trying to sort out what to do with this information, in terms of saying, I've identified this vehicle as doing something compromised, how would you go about trying to distinguish between a human driver doing that and an automated vehicle doing it, and then what would you do with that, is a question that we will need to keep working on.
And kind of the point of my question was, I'm not sure you could distinguish between a bad driver and a compromised vehicle.
It could be very difficult, yeah.
Thank you.
Yeah, thank you.
Hacking cars is undoubtedly interesting, but I've got a question on your anomaly detection. One, and you kind of started to hint at this in talking about the training data and everything, but it seems to me that you're able to detect anomalies more than compromises. So how can you tell if it was a autonomous car that stopped for a squirrel versus a compromised vehicle? And then kind of following on to that, will this type of anomaly detection be more useful when it's 90% autonomous vehicles and we're looking for the guy driving the 68 Camaro acting recklessly?
Yeah. So for the first point, absolutely fair point. We are detecting anomalies at this point. It's a needed progression for the science is to try and go from saying, I've identified this vehicle as being anomalous based on this behavior, to having a good way to say, this was anomalous enough for me to think that this is worth executing on. And it's very difficult to try and take a driver's trajectory through a traffic flow and then say something about, do I think that this did something meaningfully impactful to traffic in terms of its behavior in a way that I'm going to then go and investigate it. I think that particular question needs to also work with who is the entity trying to execute this detection problem, and what are they actually going to do about these things. So perhaps it could be, we find that there is a particular vehicle make that continues to look anomalous, then that's an investigation that should be going on, and that you may not have to say this was particularly malicious. I'm sorry, could you remind me, what was the second question?
Would this be more useful later when the ratios are flipped?
The best case scenario in my mind would be we have high penetration rate of automated vehicles, and there is a centralized understanding of what algorithms those vehicles should be using, because then you could use those algorithms to understand whether they are deviating from expected behavior. We're at the worst case right now where we don't know whether vehicles are human or automated, and then we don't even know from a centralized perspective whether all the automated vehicles, what they're actually running and what we should expect from their behavior. So, yeah, great question, thank you.
And kind of a follow-on to that, beyond the flip, right, is any of the research you're doing now going to be useful in what I see as really the ultimate?
I hope it's useful.
Well, in the ultimate implementation, right? I can see its use in the short term and things, but my ultimate implementation is that when your fully autonomous car gets on the highway, it is no longer driving. The entire highway is driving.
Yeah.
It decides that you're going 60 miles, so it's going to move you over in the far left lane, so you're less of an interference with on and off traffic, and it establishes lanes of travel where high speed, medium, less medium, low speed, exit, entry traffic. Do you see that as something, A, likely to happen, and B, achievable using some of this science you're working on now?
Ooh, great question. They should hire you at the DOT. I think that is exactly where it should go. I think a lot of people believe that's where it should go. I think that there's plenty of exerted effort to try and bring us towards that, but I think it's less a technology question and more a political question in terms of trying to have work between manufacturers and government and things like that. I honestly couldn't. It's a great question. I couldn't say whether I think it will or won't happen, but it's exactly, every transportation engineer wants that. It's unclear whether it will happen. I think a really important part of, in general, intelligent transportation systems is that we need to have algorithms that are able to analyze them for high assurance. And so anomaly detection and understanding whether there are compromises is surely one of those pieces that I would love if they wanted to talk to me about that. And I would point out that even in the context in which all the vehicles think they're talking to a centralized agent telling them what to do, we're still going to probably have these kinds of emergent behaviors where if something goes wrong, it's still going to have these rippling effects. So,
Yeah.
As a security engineer, that's a nightmare for me, right? Because as a V2 vehicle to vehicle or V2I is growing, and if they're not connected properly, once you compromise one, it's a snowball effect. You compromise everything. So I think it's like a happy medium to figure it out, that are we solving a traffic problem or we are causing a security incident? And to your point, it's mostly of a political problem.
But I think what I took from George's last comment, is that what I see here is you're doing what I consider to be the really important work now, is developing a methodology for detecting anomaly. So when you move into a fully autonomous, the highway is controlling the traffic, if you keep that system in place, so then you assume breach and you can spot it when it starts to happen. as opposed to waiting until you got 40 dead people and 50 cars wrecked.
Yeah. Yeah, I think we're at time, but I'm happy to answer any more questions outside. So thank
Thanks,
you very
everyone.
much.
Cheers.